Hi everyone! In this video, we will talk about Fastbin used after free vulnerabilities. In previous weeks, we've talked about Tcache used after free vulnerabilities. On a high level, such vulnerability can make attacker being able to overwrite the metadata stored in the free chunk so that a free chunk inside the Tcache bin will be able to point to another part of the chunk. And that chunk is a victim chunk, and then that chunk can be faked and articulated by attacker. Fastbin turns out that also has such kind of vulnerabilities. Suppose that we have Fastbin, and we already have a Fastbin layout in such a way, and an attacker can use a fake chunk to contain a victim memory, and then have the free list in Fastbin to connect to the fake chunk. In this case, when the chunk is reallocated again, then this chunk can be controlled by attacker, and from there, attacker can overwrite a victim memory, such as a malloc from the global offset table. We can summarize the process into two steps. The first step is to identify a fake chunk, and then the second step is to link that fake chunk to an existing free chunk in the Fastbin. Recall that for Tcache, when we identify fake chunk, the way that we work is that we first identify the victim memory that we want to overwrite, and then we just copy paste that memory address to the metadata of a free chunk in Tcache. However, for Fastbin, this condition is going to be more restricted, and therefore for us, when we find a fake chunk and when we create this fake chunk according to a victim address, it has to satisfy more condition. In terms of this step, identify fake chunk, a fake chunk should satisfy both conditions. First, it needs to include the victim memory. And this is apparent because only when the victim memory is included that we will be able to allocate this chunk containing the victim memory so that we can overwrite the memory. Besides victim memory inclusion, another condition is that the start of the data, which is the forward pointer when the chunk is freed, has to point to either 0 or another chunk that will ultimately point to 0. If you remember, for Tcache bin, we don't have to have this specific condition. And the reason why Fastbin have to satisfy this condition is that there is a specific process for Fastbin, which is refueling Tcache bin that requires this specific condition. If this condition is not met, then during the refueling process, there will be a segmentation fault popping up. So after we identify a fake chunk, then the next is to connect that fake chunk to an existing chunk inside a Fastbin free list. And this requires us to take advantage of a use after free vulnerability so that we can add the forward pointer so that the forward pointer will be able to point to a fake chunk. After we successfully finish the first two steps, then we need to consider how to trigger the vulnerability. Because ultimately, the goal for us to control the victim memory. Even though we have created this victim memory associated with a fake chunk that has connected to the Fastbin free list, we still need to get that control. So here's the following steps that you need to do in order to really control the victim memory. After you link the fake chunk, then the first thing that you want to do is to empty Tcache bin. In order to do that, you want to use malloc, because every time when malloc is initiated, it will first check if there is any chunk is available from Tcache bin. You may want to do malloc for multiple times until Tcache bin is empty. If there are 7 chunks in Tcache bin, then you want to do that for 7 times. Now let's suppose that there are 7 elements in Tcache bin. So we do that for 7 times. And after that, Tcache bin is empty. And next, what we're going to do is we're going to do malloc again. And this time, again, glibc will check if Tcache bin is empty. And if Tcache bin is empty, it will go check if Fastbin has any chunk available to be reused. And of course, in this case, the answer is yes. So glibc will start to use the chunk coming from Fastbin. The way that glibc, it will use the first chunk coming from the Fastbin and return that chunk to malloc. And this is not AND yet. After that, glibc will refuel Tcache bin by the chunks in Fastbin. And the way that works is as follows. Suppose that we have a pointer, and then glibc is going to use this pointer to scan over the list in Fastbin. So it will start with the first element after what we just returned for malloc, and then we're going to put that into Tcache bin. And pay attention that for Fastbin, this forward pointer always points to the start of a fake chunk. However, for Fastbin, it changes in the way that the pointer will point to the forward pointer, which is the start of the data part inside the chunk. And then it will keep scanning the elements in Fastbin. So in this case, it's going to be the next one, which is going to be the victim one. Then glibc is going to move that into Tcache bin as well. And Tcache bin is first in, last out. So when the chunk is moved from Fastbin to Tcache bin, it will always just move it to the head of the Tcache bin. In this case, that's why right now you will find that the order of Fastbin got just reversed. So in Tcache bin, the fake chunk is going to be in front of the previous chunk that we are overriding, we're editing in Fastbin. And then this entire process continues. There will be more chunks appended and inserted at the start of Tcache bin list. And the entire process stops until the pointer found at 000. And this is exactly the reason why when we fake a chunk, we want to make sure that this chunk list will end with 00. Because if it doesn't end, if there is a like a dereference error throughout this entire refueling process, then the refueling process will raise an error, and the entire glibc mallocing process will raise an error. And you don't want that to happen in order to make your attack successful. All right, at this point, we managed to move all the chunks from Fastbin to Tcache bin. And our victim memory still inside the fake chunk, and the fake chunk is a part of the chunk inside the free list of Tcache bin. And then we're going to do similar things that we have done with Tcache bins used after for vulnerabilities, which is to malloc more chunk so that the Tcache bin's free list chunk will be consumed through those malloc. And two, we get this chunk returned by a specific malloc. And here it depends on the number of chunks that you inserted over here. So if there is no chunk over here, then all you need to do is to do one time of malloc. But if you do have some, chunks after your fake chunk, when you insert a chunk here into the Fastbin, then you will need to have more times of malloc in order to get the fake chunk. Cool. That's pretty much for Fastbin used after free vulnerability. In summary, to take advantage of a Fastbin used after free, you need to identify a fake chunk that satisfies two conditions. One is that the victim memory is inside the fake chunk, and second is that the forward pointer field in the fake chunk will point to either 0 or another chunk that will ultimately point to 0. After you identify the fake chunk, the next step is to connect that fake chunk to any element inside the Fastbin. And then next, you need to use all the chunks coming from Tcache bin so that you can amplify the Tcache bin's free list. And then you're going to call malloc again so that Fastbin's chunks will be used to refuel Tcache bin. And finally, you need to call malloc for a couple of more times so that you will be able to get the fake chunk through a malloc. Turns out that finding a usable fake chunk is not that easy. And in fact, finding a fake chunk that contains malloc at global offset table turns out to be almost impossible. In this case, we're not going to use the global offset table as the victim memory. We're going to use another part of the memory, which also contains function pointers. And that field is called a malloc hook. Malloc hook is in the data segment of glibc. In the next demo, I'm going to show you malloc hook, and I'm going to show you how to utilize the malloc hook to achieve the attack of Fastbin use after free vulnerability. Now let's work on a demo together. We're going to reuse the service program that we had before, the interactive one, that a user, or say a client, can specify the memory operations according to the different options from the menu. And then user can take advantage or create a use after free and double free those different kinds of vulnerabilities. And this time, which is slightly different from previous time, that we're going to disable Tcache vulnerabilities, but we still have the vulnerabilities in Fastbin. So in this video, then we're going to try to use our current knowledge to take advantage of a use after free Fastbin vulnerability. We're going to reuse the template that we had before, which is the program that is composed of a couple of utility functions. Those are the utility functions that we can use to interact with the service. So there are malloc, free, edit, exit, and list pointers. And right now I'm leaving lunch attack this part blank. In this video, we're going to work on lunch attack together. Usually when I write attack, I will first start with an outline, because if you don't have an outline and when you just write code line by line, for me, it's very easy for me to just get lost. So I usually prefer writing an outline before I write actual code. And I'm going to use the slide over here so that we can have a more concrete and more straightforward way to look at what's inside during the interaction with the vulnerable service. So first, let's try to come up with the attack. If you still remember, in the beginning of the video, we talked about multiple steps. And the first step for us is to identify a victim place so that we can create a fake chunk. However, before that, we also need to make sure that there is content in Tcache bin and Fastbin. So I will write this as step 0, which is to prepare for Tcache bin and Fastbin. And then the first one for us is to identify a fake chunk. Second step is to link the fake chunk to Fastbin free list. And then the third one is to amplify Tcache bin. The first part is to do malloc again, so that in this case, the first chunk will return back to malloc, and then the rest of the chunk inside Fastbin will be refuel Tcache bin reversely. I will call this Tcache refuel. And then pay attention that this is reversely. After that, for example, this is the way that we Tcache refuel reversely. And then after that, we need to do malloc again for multiple times so that we will be able to get the victim memory inside the fake chunk. Malloc to get fake chunk. And after that, it will be similar to what we have done for Tcache use after free, which is we're going to overwrite the value inside the victim memory. And then the next, which is also the final one, which is to trigger the vulnerability by calling the victim pointer. This is 8 steps. And then we're going to use Python code to fill them. So the first one is to prepare for Tcache bin and Fastbin. So the way that we need to do is to first, we need to malloc a bunch of bins, and then we need to malloc them for more than 7, because for Tcache bin, the number of chunks in Tcache bin in maximum is 7. So we're gonna just put some number of bins, and here we need to make sure that the number of allocated chunks is greater than 7. Here I'm just gonna allocate 10 bins. All right. And then the next is to freight them. So when we freight the first 7 chunks, those chunks will go to Tcache bin. And starting from the 8th chunk, it's going to go to Tcache bin. Sorry, it's going to go to Fastbin. Okay, now we're going to start the actual attacking part. The first step is to pick up a fake chunk. Suppose that we identify victim memory, which is the place that we want to overwrite. And right now I'm going to put a random number for now. And then later we're going to change this. And then the next is we need to find the fake chunk address, which is always the victim memory minus hex 10, which is 16 bytes. And right now, let me just go to this place, right? So this is the first step. So we need to identify a fake chunk, and also we need to identify the victim memory. And if you still remember that to identify the fake chunk, there is some requirement to the identified fake chunk. So let me go this slide. This is the condition that we know that we need to satisfy in order to make the fake chunk reasonable and in order to make the attack successful. So a fake chunk should satisfy that include victim memory, which is good. We already finished that. And then the second condition is that the forward pointer, which is going to be the victim memory, where victim memory points to, needs to be 0 or points to another chunk that will ultimately with the forward pointer as 0. So the question here is that can we make the victim memory storing the value of 0 or another like pointer that will ultimately contain a chunk that with the forward pointer equal to 0. If you remember, for Tcache attack, what we put here for victim memory is the global offset table. of the malloc, right? So what we have originally is the global offset table with malloc. However, we know that for global offset table, there's no way for us to make this specific location equal to 0, because it will either store the actual function pointer of glibc's malloc, or it will store the instruction pointer that will resolve the function pointer of glibc and then store it back to the global offset table. So we know that there's no way for us to make this 0. Then how are we going to find another possible function pointer that may start with 0 so that we can use it to overwrite? Turns out that glibc has a nice field which is called malloc hook. Malloc hook is a specific field in glibc which allows users to modify the behavior of malloc, realloc, and free by specifying an appropriate hook. And users or someone that is going to change malloc hook can use these hooks to help debug information. Also, you can use that to do like any kind of dynamic memory allocation. So originally, malloc hook is designed to facilitate users to track the malloc and then get information or do a dynamic debugging, instrumentation, etc. However, an attacker can abuse malloc hook by pointing malloc hook to a malicious function, such as the winning function. So at the beginning, malloc hook is assigned as 0. When malloc hook is 0, there's nothing going to start over there, and then glibc will just go for its default hook function. Therefore, it is feasible for us, since it satisfies the condition that the victim memory stores the value with 0. To get the address of malloc hook, we could use the punctual utility, which is with the ELF. And if you use the elf object, you could just do elf.libc.symbols, and it will return the value of a malloc hook. However, you need to pay attention that here, since the libc is linked dynamically, the symbol of malloc hook is only the offset of glibc. So you still need to figure out where libc is loaded, where is the base address of libc when the process is running. For now, let's just assume that the program is ASLR disabled, so that every time when a libc function is loaded, it's going to be in the same address. So for now, I'm going to just put the fake value so far, and later on, we can get the value of the base address by locally running it with ASLR disabled. Right now, I'm just put a random value. And then for victim memory, it will be equal to the base address plus the offset that we can extract from the elf object. And then the fake chunk address should be the victim memory minus hex 10. All right. Now the next is to link the fake chunk to Fastbin for a list. So we already finished this step, and then we're going to link it to somewhere. If you see in the picture, you know that there are some options for us. We can link this location here. We can also link this fake chunk to the end of Fastbin. We can just link fake chunk to any of the chunk of the Fastbin. So we probably need to decide which exact chunk in the Fastbin that we want to link. Right now, let's just assume that we're going to link into the second Fastbin. So as it shows over here in the slide, the fake chunk will become the third chunk in Fastbin list. And then in this case, here, when we write the program, we need to use edit, and we're going to put this is going to be the 8th one, right? Because for Fastbin, when a chunk is added in, it will always add in the head of the Fastbin. So for the index perspective, here is going to be index 7, and then 8, and then 9. So here is going to be the 8th one, the 8th chunk. So that's why I put 8 over here. And then I'm going to edit that, put the address of the fake chunk address. And again, because right now we're dealing with Fastbin, and in Fastbin, the forward pointer point to the start of the chunk. That's why fake chunk address is equal to the victim memory minus hex 10. However, for Tcache bin, when we are faking it, we actually want to make the fake chunk address starting with the victim memory instead of having this value subtracted by hex 10. This is due to the nature of the forward pointer setup in Fastbin and in Tcache bin. After that, then we're going to amplify Tcache bin. So we can consider that as 2 steps. The first step is that we're going to do malloc for 7 times so that we're going to amplify the entire Tcache bin. And then the next is that we need to have those Fastbin chunks refuel Tcache bin. And the way that it works is to use malloc. So here we need to do malloc again. And in the case, after this malloc, we will be able to have those chunks moving from Fastbin to Tcache bin. And also pay attention here that when the refueling happens, it's going to refueling Tcache bin in a reverse order. So suppose that in Fastbin right now, if the order is the green chunk followed by blue chunk followed by the victim chunk, then when this step's malloc is called, the green one will be returned for the malloc, and then the orange one, which is the victim chunk, will go first in Tcache bin. Orange chunk will become the first one, and then the blue chunk will become the next chunk in Tcache bin. Okay, and then the next for us is to malloc again in order to get fake chunk. So we should do malloc again with the value of hex 20. At this point, you may sense that there's something wrong. Here is why it's wrong. If we're doing malloc again now, then for victim, which is malloc hook, glibc will check the value of malloc hook. However, for Tcache bin, since we are refueling it, the forward pointer of the victim chunk will point to the next chunk, which is the blue chunk, right? And then forward pointer at this case, and then forward pointer is exactly the location of malloc hook. So malloc hook will contain a value, which is the memory of this chunk. At this moment, malloc hook is no longer be equal to 0. So if we call malloc again now, then malloc hook will go to this. So if we call malloc now, then glibc will consider this address as the start of a malloc hook function. However, we know that this is not. This is just like a piece of chunk in heap. And we don't want malloc hook to wrongly indirect it to somewhere that we don't want to. So how are we going to edit that? You can pause the video to think about this for a second, and then resume the video to follow with me. We can resolve this issue by linking the victim chunk to another place. So instead of linking the fake chunk to the second chunk, we're going to change that to link to the first chunk in Fastbin. In this case, when we do malloc again in the 4th step, the first chunk will return to the malloc, and then since there is only one chunk left in the faked Fastbin free list, we'll have such layout in Tcache bin. So this victim memory, this fake chunk, will be the only chunk that is appended into Tcache bin. And here will remain 0, which is the victim memory, which is also malloc hook. Okay, so in this case, that we need to change the second step. And then we need to change this from index number 8 to index number 9. And this is because in Fastbin, when we stored it, it's going to be in a reverse order. So here is index number 7. This is index number 8 and index number 9. And that's why when we change this value, we want to here link the fake chunk to the index of number 9. Okay, and now let's continue. The rest is that we're going to overwrite the victim memory. So we need to edit this specific memory, and we need to overwrite that with the value of winning function. And here we need to reason about the index of the current chunk. So here we have the chunk with index from 0 to 9. And then after that, we have mallocated again, right? So that is going to be index from 10 to, so there are 7th, so it's going to be 10 to 16. And after that, this is index 17. And here is index 18. So the index that we want to put over here for this added, which is also overwritten, is going to be 18. And then we want to change that value to the winning function. After that, we just need to trigger this again, and then we can just put interactive over here. And we can just put interactive to interact with the servers and making sure that if there is anything wrong. And now let's figure out how to get a base address. So here's the way that you can use to figure out the base address. In the main function, if you're going to use Pong2 to initiate the process, then you can put ASLR equal to false over here to disable ASLR in your process. And then you can just add another interactive over here before you launch the actual attack, and then run the program. So you know that currently the PID of the service is 65070. Then you can use GDB to attach to this process. And then use VMMap to get the current base address, putting it back. Or alternatively, you can also do that after you get this PID, you could just use a cat to look into the current map of the process. Similarly, you will also be able to get this same value. Now let's go back to the program. And we already put the base address over here. Let's delete this interactive and then make the program run. Now we're at the end of the attack. We just do interactive mode and then type M2, and we get the winning function.